All right, so lesson 10.5, area in polar coordinates. So area, if you recall the area of a sector, that was 1/2 theta r squared. Okay, so the area of a region bounded by a polar curve is much the same. 1/2, now theta is replaced with our d theta, and then, oh, missed that parenthesis. Our function squared, okay, our function in terms of theta is just what our value of r will be, and then bounded between theta equals alpha and beta. And our angle measure must increase from alpha to beta. Okay, and that makes sense because when we set up our bounds of integration, we know we go low to high. Okay, so let's go over the trig identities we mentioned briefly in class. So we know our Pythagorean identity, sine squared theta plus cosine squared theta equals 1. Our double angles, sine of 2 theta is 2 times the sine of theta times the cosine of theta. The cosine of 2 theta. That's where there were 3 equivalent representations. Cosine squared of theta minus sine squared of theta. 1 minus 2 sine squared of theta. And then 2 cosine squared theta minus 1. So if we think about our area formula, we're going to be squaring some function that's in terms of theta. So we'll see a lot of these come up in our integrand. So if we think about just integrating cosine squared theta, we can't do it. So we have these equivalent forms that you're going to have to be able to recognize in order to finish the integral. So if I use the identity, cosine 2 theta is equal to 2 cosine squared theta minus 1. And you'll see this when we do examples. This is what will be in my integrand, and that's what I'm going to have to replace. So I'm going to add 1 and divide by 2. So in our integrand, if we ever have to evaluate the antiderivative of cosine squared, we can replace it with an expression that we can integrate. And then similarly, using the identity for sine squared, okay, solving this identity for sine squared, I'm going to subtract 1 and then divide by negative 2. Okay, so if I just multiply my numerator by negative 1, when we use this identity, we'll keep the denominator positive. So in this video, we're not solving anything. We'll do all the integrating together. You guys are just going to set them up for me by finding the points of intersection. Okay, so find the values of theta where the curve goes through the origin. Okay, so for polar, we're finding where our radius would equal 0. Okay, so 0 equals 3 times the cosine of theta. Okay, so where does the cosine equal 0? So our values of theta would be pi over 2 and 3 pi over 2. And we'll keep it within one rotation of the unit circle, so between 0 and 2 pi. Okay, this is all we're doing today, and we'll use these bounds. These will eventually become our limits for our integral. Okay, so the second one, r equals 4 sine 2 theta. Okay, so we get 0 equals the sine of 2 theta. Okay, so now we have where 2 theta, so the sine equals 0 at 0, pi, 2 pi, and 3 pi. And remember, when we have this coefficient to the angle measure, we get twice as many values, because then we have to divide each of our values of theta by 2. Okay, and if we did 4 pi, so that would give us 1 rotation in the unit circle. Okay. All right, next one, find the values where this function goes through the origin, this curve. So when we set cosine 5 theta equal to 0, okay, so all our intervals of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. And you'll find that these are going to give us more than enough information. So I'll stop here. Okay, so then solving for theta, multiply all of these angle measures by 1/5. So pi over 10, 3 pi over 10, 5 pi over 10 would give us pi over 2, and then 7 pi over 10. Okay, and then we have the function 1 minus sine theta. So 0 equals 1 minus sine theta. So where does our sine function equal 1? That only occurs at pi over 2. And for this one, like I said, we'll set it up for tomorrow. Find for me the points of intersection where the radius is 1. So setting r equal to 1. We get where the sine theta equals 0. So that gives me 0, pi, and 2 pi. And then lastly, for the curve 3 plus 4 sine theta. Okay, so subtracting 3 and dividing by 4. All right, so now when we think about solving this, this would be the arc sine of -3/4. Okay, and if we think about our domain for arc sine from negative pi over 2 to pi over 2, okay, so theta will be a 4th quadrant angle, okay, because that's where the sine has its negative values. Okay, that's it for today. This will set it up for us to be able to integrate in class tomorrow.